So today we are looking at section 321, which is investigating some rational functions. So we have this one problem where we're actually going to go through and we're going to look at two of our functions, and we're going to add them, we're going to subtract them, we're going to multiply them, and we're going to divide them together, and we're going to come up with how that changes the graph of those two functions when we add them together, subtract them, multiply them, and dividing. And when we divide them, that's where that rational function is going to come in. So we've kind of dabbled our feet into it a little bit. So we're just going to dabble our feet into it some more. And then we have a definition to go over about a thing called a closed set. And then I'm going to go over some properties of exponents that we've done in the past, but I know in the review preview there's quite a few problems on there that have to do with exponents. So I just want to make sure that we have all of our properties down, we have them in our notes so we can refer back to them, and then we can work on a few of those examples. So problem 57, they gave us a whole slew of different problems to work on, right? And instead of going through all of these, because normally we would break into teams and in the classroom into groups, and then each group would pick one of these and kind of go through the same activity. So I'm going to do one of them. I do encourage you to go back and pick one and go ahead and do it on your own, just to make sure that you are able to add, subtract, multiply, and divide, and kind of see how those differences affect all of these little graphs. So this first one is the one that we're going to focus on in class, the one that I'm going to do. So if I do this one, then you guys pick a different one to work on. I think that's the one I picked, wasn't it? Yes, it was. I had to double check myself. So let's get to it. So I just went ahead and I just wrote those two out. In that one, that f of 1 and g of 1, the only reason, that that's on there is if, and it doesn't affect the problem at all, it's just saying like this is f1, g1, so they're putting those ones together. This is the second problem, so those are the 2's. This is the third problem, so it's the sub 3. But it doesn't affect the equation, the function, or the problem at all. All right. So the first thing they wanted us to do is they wanted us to add these two functions together. Right? So they wanted f of x plus g of x, right? And if we want to, we can put the little ones in there, those subscript ones if you want to. So to add these two together, you're just taking your function f of x, which was x minus 2, and they want you to add onto that 2x plus 3. So what are we going to come up with? We're just going to add like terms. So we have x plus 2x, which is going to give us 3x. And then negative 2 plus 3 is going to give us a positive 1. So we end up with this 3x plus 1 as our little function. And when we look at this, and it's like what kind of, and they want us to make a prediction on what the graph is going to look like. Well, hopefully we know that this is going to be a linear graph. It belongs to the linear family because our exponent has a degree of 1. It's going to go through the y-axis at 1, and it's going to have a slope of 3. Then they want us to subtract. So they want us to subtract f of x minus g of x. So our f of x was x minus 2, and they want us to subtract 2x plus 3. So what are we going to get? X minus 2x. So x minus 2x is going to give us negative x. And then negative 2 minus a 3. Negative 2 minus 3 is negative 5. So again, we are going to get a linear function. It's going to cross the y-axis at negative 1, and it's going to have a slope of negative 1. So when we subtracted, it ended up changing our slope to a negative on this problem. Then they want us to multiply So to multiply, they want us to do x minus 2 times 2x plus 3, right? So options, you can use your distributive property and make sure you're sharing with everybody, or we're going to do the area model. So if we do the area model, I'm going to do x minus 2 on top, 2x plus 3 on the side. Doesn't really matter where you put it. We're going to multiply these, and we're going to get the area of this box would be 2x squared. The area of this one would be negative 4x. The area would be 3x, and the area would be 6. So we can combine our like terms, and what do we have? 2x squared minus x minus 6. So when we look at this one, because we can see that our degree is now a 2, it is going to be a quadratic. And our quadratic, it's going to have a stretch factor of 2, so it's going to be a little on the skinnier side, and it's going to cross the y-axis at negative 6. Granted, we could go through and solve these for 0, and we could find out where it's going to cross the x-axis as well, but we'll leave that one for now. And then the last one they want us to do is to divide. Well, I guess I could have wrote that on there, right? So they want us to divide f of x over g of x. So f of x was x minus 2 divided by our g of x, which was 2x plus 3, right? So common mistake that some students will make is they'll think that they can cross off these x's, and we can't. This whole entire numerator is one quantity. This denominator is one quantity. The factors would have to be exactly the same to be able to cross them off of top and bottom. So you always look to see if there's something you can factor out of this that might be able to match up so you can cancel, but on this one, we do not, right? This is what we call a rational function. Right, or a rational expression. Rational is like a ratio, so you have one over the other, which we have like with the fraction. When it comes to our rational functions, we notice that we have, this becomes rational because we have a variable in our denominator. So when it comes to our denominator, we have to be careful. We know that denominators can never equal 0, right? We can't divide by 0. We can't pull 5 apples out of a basket that has 0 apples in it, right? So our denominator can never be 0. So when it comes to graphing, these are those asymptotes. So we're going to look at our denominator and we're going to find out where there is an asymptote. So we know that our denominator cannot equal 0, right? So I usually just 2x plus 3, and I say that it equals 0. Even though I know it can't equal 0, it's going to tell me where my asymptote is, right? So then I'm going to subtract 3 from both sides. I'm going to get 2x equals negative 3. Then to get x all by itself, I'm going to get negative 3/2, right? So what this is telling me is that on my graph, when I make my graph, where x is negative 3/2, which would be like at 1.5, negative 1.5, there's an asymptote, right? So we kind of, remember we would draw like the little dotted lines, and it's a barrier or a fence, right? You can get really close to it, but you can't cross it. So what they did on all of these problems was, after you guys came up with your new equations, I guess I could have done these in all the same color, right? So we have this for our linear when we added, this was when we subtracted, this was when we multiplied, and when we divided it stayed exactly the same. But we now know that where that asymptote is, so we can look at that when we do our graph. So they have the little tool on here, and it'll take you straight to Desmos, and it has that for every single one of the problems. So when we go ahead and click on that, so this brings you straight to Desmos, and it brings you right to that problem that we were working on. We were looking at when f of x was x minus 2 and the 2x plus 3. Every time you click on the different problem, it takes you, these f and g's will change. I went ahead and jumped into the game. These are left blank, where number 1, add the functions together. This was blank, and I just went ahead and fed it in our answers that we came up with from the first page, just to kind of save a little bit of time. So if you want, you can click right on the little circle. Why won't it do it? There we go. That was our f of x, and we see that f of x, it crosses the axes at -2, and it has a slope of 1. Up 1, over 1, slope of 1. Right? We can click on our g of x. We can click on our g of x. If we wanted to, we could even click off of our f of x if we wanted to, if we just wanted to see g of x, or we could click in so we can see where both of those are, right? So these were the original two that we ended up having, right? So I'm just gonna turn those two off. We said that when we added them, we ended up with the 3x plus 1. And we said that 3x plus 1, when we talked about it, we said that it was going to cross at 1, and it's going to have a slope of 3. 1, 2, 3, and over 1. So we graphed it correctly, right? Then we went ahead and we subtracted. And we said that this gave us a slope of -1, and it crossed at -5, right? And that one, it holds true. The other one we said when we multiplied, number 3, when we multiplied, we ended up getting a quadratic. So here's our quadratic that we ended up graphing. All right, and that's kind of what we predicted it would look like, right? We could even follow the vertex if we really wanted to get fancy. And then on the last one was our rational expression, right? Where we said that we had the asymptote. And so this is what the new kind of piece was, is how that looks, where we have that fence that we're getting really, really close to, but we're just not quite touching it. This one actually has a horizontal asymptote as well, and we'll get into those kind of discussions later, and that has to do with having an x on the top and the bottom of the same degree, but we'll get to that at another time, right? All right, so make sure you guys are going back and trying one of those problems or more than one of those problems on your own from back here, and just make sure that you're able to go through those same steps that we went through on the notes. Okay. On problem 61, they just talk about this thing called the closed set, and I just want to go through and explain what they mean by it. Sometimes reading the definitions are like, what? Right? So they say like a closed set. So whole numbers, positive integers, and zeros. So whole numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? No negative numbers, no decimals, no fractions. They say that this is said to be a closed set under addition. So what it's saying is, it's like if you take a whole number and you add them together, guess what kind of number you're going to get? A whole number, right? So pick a whole number. What'd you say? Sorry, I didn't hear you. 7? 7. Yep, so 7 plus, I don't know, let's say 3. 7 plus 3 is 10. Whole number, whole number, whole number, right? So it holds true when it comes to addition. Whole number is not closed if you subtract two whole numbers. So can you come up with an example of subtracting whole numbers and where we don't get a whole number? So, right, this one we got a whole number. What if we just did 7 minus 3? What's 7 minus 3? That's 4. So is that a whole number? Yeah, that's a whole number. What if we switched them around and we did 3 minus 7? What do we get? Yeah, we get -4. And this is not a whole number, right? And so this is what they're saying, so that it does not always apply under subtraction. Right? So in order for that closed set to always happen, it always has to be true. So we can find examples in which it is true, but it has to hold true for all examples. And here's an example where it's not, right? I wonder what would happen if we multiplied whole numbers. If we multiplied, let's say 7 times 3, what do we get? 21. Is that a whole number? Yeah. What if we did like 3 times 7? We still gonna get a whole number? We're still gonna get a whole number. So it's closed under multiplication, right? These two are both whole numbers, right? What about dividing? What if I did, I don't know, let's say 4 divided by 2? That's a whole, 4 is a whole number, 2 is a whole number. 4 divided by 2 is 2. That's a whole number, right? Can we think of an example where we don't get a whole number? Yeah, we could use our 7 over 3 as an example, right? 7 divided by 3, that's a whole number divided by a whole number, but we can't reduce it, and if we were to figure that out, that would actually be a decimal. That'd be what? Approximately 2.3, I believe. So this is not a whole number. So it's not a closed set under subtraction, and you can't get a closed set under division, because on those two it doesn't always work. So they just want to throw that definition out for you, because I bet you it's going to come back to us one day. All right. So like I said at the very beginning, in the review and preview, they give some problems that have to do with properties of exponents. Oh yeah, you guys have a quiz on Thursday. Perfect time to announce that. On Thursday you guys have a quiz, and exponents will be on the quiz. So the quiz will be over pretty much like chapter 3, 1 through and 3, 2, because we haven't had a quiz yet over chapter 3. So exponents, these property of exponents will definitely be on the quiz on Thursday. So I wanted to go through and we go through these little properties. So properties of exponents. And these are good to have in your notes so you can refer back to them when it comes to working on your guys' assignments. All right. So let's let's talk about negative exponent, right? So if we have a to the negative 2, we never want to leave our exponents negative. So our exponents always have to be positive. So when we are given a negative exponent, we need to find the reciprocal or flip it. So this would be the same thing as 1 over a squared, right? Or another example would be if we had 1 over a to the negative 2. Again, we have a negative exponent. We need to make that a positive exponent, so we need to flip it or do the reciprocal. So it's actually going to come up to the top, and we would have a squared, right? There is the 0 exponent property, which just says that any number raised to the 0 exponent is always going to equal what? Yep, 1. Good job. Is the product property. Product means multiply, so we're going to have, let's say, x raised to the a times x, the same base raised to the b. That's going to be where we just add those exponents together, so that would be a to the x plus b. So for example, if we had, let's say, x to the 3rd times x to the 4th, that's going to equal x to the 3 plus 4, which is x to the 7th, right? The 4th one is the power property. So the power is going to be like the exponent. So this is, let's say we have some base x raised to the a, but then it's also raised to the b power. So when we have them in like parentheses where they're raised to another power, we'd be multiplying those. So that would be x to the a times b. So for example, I'm even going to throw a 2 in there. So let's say in parentheses we had 2 x to the third all raised to the fourth. So that's ultimately saying you're multiplying that whole entire thing out 4 times. So 2x to the third times 2x to the third times 2x to the third times 2x to the third. So when we have things raised to the first power, so like our 2 is technically raised to the first power, we never write the 1 in there. If it's better for you to write it in, then write it in, right? Because now when it comes to this 4, because we have to multiply by, we just got to make sure we share it with everybody. So this is going to equal 2 to the 1, right, times 4 times x to the third times 4. So 2 to the fourth, 2 times 2 times 2 times 2 is going to get us to 16, and then x to the 12th. Right. The fifth rule, or property, is the quotient rule, or the quotient property. Quotient means divide. So let's say we have like x to the a power divided by x to the b power. So since they have the same base, this would be equals x to the a minus b. So for example, if we had x to the fourth over x to the third, this would be x to the top minus the bottom, which is going to give us x to the first, or just x, right? Getting to some more of the little fancier ones, there is the power of a product. So number 6 is we're going to go with a power of a product. So this would be, kind of getting a little squashy in here. I'm going to drop down a little bit. So this would be if we had, let's say, some base a raised to the, x raised to the a power, and then y raised to the b power raised to the c power. So this is really a lot like the power property, especially on the example that I did. This is pretty much saying that whatever is on the outside, you just got to make sure you share with everybody on the inside. So this is going to end up being x to the a times c, y to the b times c. All right. And then the last one that we're going to go over, my goodness. Okay, stop. Number 7 would be the power of quotients. So the power of quotients. So quotient means divide, right? So this is saying if we had, let's say, x raised to the a divided by, we'll stick with our y to the b. But this whole entire thing is raised to the c power. So we, again, just have to make sure that we share our c with everybody. So this is going to become x to the a times c divided by y b times c. All right? So this is a good slide to make sure you have written down in your notes with some examples on there. So that way you can refer back to it, right? All right, so we're going to do a handful of examples of using these little properties just to make sure that we have a good little understanding on it, right? So we want to be able to simplify all of these, and we know that it's simplified when all of our similar terms, when all similar terms, are combined. And number 2, when there are no negative exponents. Those are the 2 big keys when it comes to simplifying our problems and making sure that they're simplified as far as they can go. All of the like terms or similar terms are all combined, and then there's no negative exponents. So let's say we had example 1 would be 2x to the 3rd, y to the 6th, all raised to the 4th. So we can go back to our products or our properties to see if there's anything that looks kind of familiar to this, and I'd say this probably looks a lot like number 6, right? So on number 6, we just need to make sure that we are sharing that 4 is going to all of my numbers on the inside. Again, if it helps, you can make it 2 to the 1st, right? So this is going to give us 2 to the 1 times 4, x to the 3 times 4, y to the 6 times 4, right? And we can clean that up. 2 to the 4th, hey, we just did one like that, didn't we? We came up with 16. X to the 12th and y to the 24th, right? No negative exponents, and all of my x's are combined, all of my y's are combined, so I am finished with that problem. What about if we had, let's say, negative 6 x squared y to the 5th, and then in parentheses 3x y to the 3rd. So looking back at our properties, this looks a lot like the product property, number 3, where we're multiplying these together. So we're going to multiply kind of piece by piece, right? Negative 6 times 3 is going to give us negative 18. And then we'd have x squared, and then we have x, and again, if you want to write that to the 1. So what are we going to do with these ones? Because this is the product property, we're going to add them, right? And then y to the 5th plus the 3rd. So simplifying that, we have what? Negative 18, x to the 3rd, y to the 8th. All right. Let's say we had 100 x to the 12th, y squared, divided by 20 x to the 16th, y to the negative 4. Right? So whole numbers to whole numbers. So what's 100 divided by 20? We know that that's 5, so I'm going to give you the 5, right? So then when I look at the x's, this is division, so it's quotient. So we are going to use our quotient property, like this one, and our quotient tells us that we subtract top from bottom, right? So we would have x would be 12 minus what's on the bottom, 16, and then y, what's on top, 2 minus what's on bottom, negative 4. So that's going to give us 5. X to the 12 minus 16 is, yep, negative 4. Y to the 2 minus a negative 4 is going to become a positive, so it's going to be 2 plus 6, or 2 plus 4, which is going to give us 6. So are we done? Well, are all of our similar terms combined? Yep, all of our x's and y's and whole numbers are all combined as much as possible. Do we have negative exponents? Oh, we do. That x has that negative exponent. So when we have negative exponents, we do like the reciprocal, right? So this would end up being 5. And then on the bottom, we would now have x to the 4th. And on the top, we would have y to the 6th. Now we know that we are done because we have no negative exponents. All right? All right, last example for the day. So let's say we have in parentheses, in the numerator, I'm going to have 5x, and in the denominator, I'm going to have y to the 4th, and I'm going to raise all of that to the negative 2 exponent or degree. So you have a couple options when it comes to doing this problem with that negative exponent. You can go ahead and take that negative to everybody and share with everybody to start with, and then do your reciprocal or flipping it over for your negatives. Or you can deal with the negative right off front, because that negative goes to the numerator and denominator. To get rid of the negative, you're going to be flipping both of them over, right? So I'm just going to start by getting rid of the negative. So to get rid of the negative, I'm going to do the reciprocal. So y to the fourth is going to come up to my numerator, and 5x is going to go to my denominator, and now it's going to be to a positive 2. Now I'm going to take my 2 and I have to share with everybody, right? Just like we did up here when it came to our power of quotient, right? It's getting shared with everybody. So I'm going to have, gotta get back to the pen. Y to the 4 times 2 over 5. If I need to, I can write it to the first, right? And then I'm going to multiply that by 2. And then x, I can put that to the first power if I need to, and I gotta times that by 2. I gotta share with everybody. So then now what do I have? I have y to the 8th over 5 squared. What's 5 squared? 25. And then x squared. Yep. So my x's and y's are all combined as much as possible. My whole numbers are simplified as much as possible, right? And no negative exponents, so I am good to go. Very nice. All right. Last but not least, when it comes to our square roots are the same thing as raising our base to a fraction. So if we have the square root, or just the root, some root, we're going to say a root b. I'm going to make that a little bit bigger. That was a nice little square root, but I'm going to make it a little bigger, right? To a b. And that could be a 2, a 3, a 4, a 5, a 6. It could be any number greater than 2, 2 or greater, right? And that's going to some number raised to the a, right? So if we don't want to write it as a square root with that symbol in there, the formula for this is x to the a divided by b, right? And it goes just the other way too. If I gave you a fraction and I wanted you to write it as some root, well, x is going to be your base, right? That x is going to be raised to the a power, and you're taking the b root. So a lot of times, or not a lot of times, so if we actually looked at like the square root of 4, so there's a little parts on this. So again, 4 is technically raised to the first power, we just never write it in. And on square roots, we really never ever write that little 2 in there, but technically there's a 2 in there. If there's no number in there, it's a 2. So this is the same thing as 4 raised to the 1/2, which is going to give us 2, right? So today, we're really just focusing on taking like these fractions and being able to like rewrite them as radical numbers. So let's go through a couple examples. So if we had, let's say, 25 raised to the 1/2, we know that this one, we're going to have the root, our base is 25. It's raised to the first power, and we're taking the second root, right? Because this is our a and this is our b, right? This is our a, this is our b. Just put little arrows on there so you don't think it's minus, right? Let's say we had negative 81 raised to the 1/4. Since it's a fraction, we know it's a radical. Our base is negative 81. Our power, it's going to be raised to the exponent of 1, and our root is 4. Right? And you could go through and solve some of these on your calculator, or if you even knew, like we know that, I would hope we know that the square root of 25 is plus or minus 5, but we're not getting into that right now. We just want to make sure that you can be able to write these in both of those equivalent forms, right? 27 raised to the 4/3. Since it's a fraction, we know it is a radical with a base of that whole number 27 raised to the 4th, with a root of 3, right? I think you guys are, we're going to throw one more on there, right? 4 to the 3/2, right? We know that it's a radical with a base of 4 raised to the 3rd with the root of 2, right? And then we can even get more fancy, and we can actually put a whole problem like together. What about if we had 20x to the 4th over 5x to the 3/2? So on this one, we need to first focus on our exponents, right? Our properties of exponents to see if we can simplify this. So I can do 20 over 5. 20 over 5 is 4. I have a quotient property going on, right? My x's are over each other, so I know I have to subtract them. So it's going to be x to the 4 minus 3/2. And we're like, oh man, fractions. Fractions are our friends, right? To subtract fractions or to add fractions, we got to have a common denominator. So our common denominator is going to be 2. So we're going to have 8 over 2 minus 3 over 2, right? So what do we have? 4x to the 5 over 2. So the big part on this issue, or this problem that we wanted to focus on, is why we gave it to you, was this 5/2 only refers to the x, right? This 4, it's 4 times x to the 5/2. Granted, if this was all in parentheses, it would apply to the 4, but the way it's written, it is not. So when it comes to writing our radical, our 4 is on the outside of the radical. It has nothing to do with the radical. But now that we know that we have a fraction exponent with x, we know that we're going to have a radical. We know that our root is going to be x, and it's going to be raised to the 5th, and we're taking the root of 2. Right? And then that would be your final answer. Right? So you guys have a couple of problems to work on. And we have that quiz on Thursday. And so tomorrow there will be some review problems for you to work on.